Now let's drive our first two-dimensional element. It will be a bilinear membrane element. So quadrilateral will have 4 nodes. Membrane element. And in that element we will be using the bilinear shape functions. So let's first define our element. Let's draw it this way. It doesn't have to be square, it can have any shapes. Just X and Y. So that's our node 1, node 2, node 3, and node 4. So the coordinate interpolation I will be using the bilinear shape functions. Now remember that in the derivation of the membrane action or the plane stress case with the axial deformations, we said that we need C0 continuity. So C0 continuity means that a linear element can satisfy the requirements of an admissible function. So that's what we will be using. So since this element has 4 nodes, the only interpolation function that we define is a bilinear function, and I will draw what I meant by the bilinear function. But let's first write the coordinate interpolation. That's our element coordinates is equal to I is equal to 1 to 4. Now we have the bilinear function, which I show it by Ni, multiplied by the coordinate of the element. In that case, x is equal to x coordinate and the y coordinate of a particular node. Now this n, we said that they are bilinear shape functions. So let me briefly draw them. This is our domain. And these functions, that n is equal to, the Ni is here at 1 unit displacement at 1 and 0 at elsewhere, and the variation is all linear. So that's the shape of N1. Remember that. This is the first node, second node, third node, and the fourth node. So N2, of course you can always switch the order of these functions, it doesn't matter. This is equal to 1, and the variation between the nodes or within the element is always linear. So it goes this way. And when we will talk about the implementation of this element, I will give you the equations of this N1 functions. They are usually defined in the natural coordinate system, and we have to do a mapping between the Cartesian coordinate system and the natural coordinate system. But for now on, let's say that these Ni's are defined in the Cartesian coordinate system. So this is our coordinate interpolation. Now let's also define the displacements. Let me correct this. Nodal displacements. So again, this is our element that has 4 nodes. 1, 2, 3, and 4. Again, that's the coordinate axis for this element. And the nodal displacements are defined as follows. We have a translation in x, u1, translation in y, v1, translation in x, u2, v2, u3, v3, u4, and v4. So basically this element has 8 degrees of freedom at 4 nodes. At each node we have 2 degrees of freedom, and again, for interpolating these nodal degrees of freedoms, I will be using the shape bilinear shape function. So displacement interpolation u is equal to I is equal to 1 to 4 ni multiplied with ui. And remember that the shape function that I use has unit value at the corresponding node, and elsewhere it's equal to 0. So when I multiply the nodal displacement with this shape function, I'm automatically satisfying the essential boundary conditions. So when we are at this coordinate, the u will be equal to ui. And likewise, the displacement in the y direction is equal to, again I can use the same interpolation functions. I is equal to 1 to 4 ni multiplied by vi. So again, bilinear shape functions, ni is C0 continuous. So it satisfies the essential boundary condition. It's a continuous function, one-time differentiable. So that's an admissible function. It's one-time differentiable both in the x direction and in the y direction. So let's show the displacement interpolation in matrix form. So here, displacement in x direction and the displacement in y direction is equal to n1, 0, n2, 0, n3, 0, and n4, 0. n1, 0, n2, 0, n3, 0, and 4, and I have the nodal displacement u1, v1, u2, v2, and so on. So this is our displacement field definition. Now let's take a look at this strain displacement relationship. So let's remember first, epsilon xx is equal to del u over del x. Epsilon yy is equal to del v over del y. And gamma xy is equal to del u over del y plus del v over del x. Okay, so I can just directly write epsilon xx is equal to I is equal to 1 to 4 del ni over del x multiplied with the nodal translation. And for the epsilon yy, I can write the following equation. I is equal to 1 to 4 del ni over del y multiplied by vi. And finally, the shear strain is equal to I is equal to 1 to 4 del ni over del y multiplied by ui plus del ni over del x multiplied by vi. So let's show these equations in matrix form. Here I have epsilon xx, epsilon yy, and gamma xy. That's equal to del n1, del x 0, del n2, del x 0, okay. Epsilon yy is equal to del n1 over del y 0 del n2 del y 0 del n3 del y 0 and del n4 over del y. And shear strain, now I have to do this, del x del n2 over del y del n2 over del x and this should be multiplied by the nodal displacement v1 u2 v2 and so on. And I can write this relationship as follows. The strains are equal to strain displacement relationship B multiplied by the nodal displacements. So this will be our B matrix. Now the next step is the constitutive relationship. Sorry, let me correct that. So we already derived the stress-strain relationship for the plane stress case. I will not just write it one more time, but I can just say that stress is equal to elastic modulus times the strains. Since we know that strain is equal to B times U, I can just directly write it as elastic, so not the elastic modulus, the constitutive relationship multiplied with B matrix multiplied with the nodal displacements. So we have all the relationships that we need. Now let's take a look at the element energy. I can just write it this way. the variation in the total potential energy. That's not the total potential energy. Let's start from here. The total potential energy is equal to the element internal energy minus the external energy. So let's start from the element internal energy. U element is equal to integrated over the area. Let's write it this way now. 1 over 2 strain transpose multiplied with the constitutive relationship multiplied with the strain itself, and T times dA will give me the area. So inserting this equation into the internal strain energy, we have the following. A is equal to 1 over 2 U transpose B transpose multiplied by the constitutive relationship multiplied by B and multiplied with the displacement itself and T times dA. And we know that this expression will give us the element stiffness matrix. And the external work, I will just write it for the surface load case. So integrated over the area, I have thickness, the body force or the surface force multiplied by the displacement and integrated over the area. And for the displacements, I can just put our displacement interpolation, which is this one, or we can just simply write it as follows. U is equal to N times UI. So from that, if you just plug it into that equation, I have area T times F body multiplied by N transpose, and I have the nodal displacements this time. And you have to integrate over the area again. Okay, so we have the expressions. Now invoking the stationary condition, that should be equal to 0. So the first variation of the total potential energy. So this tells me that U epsilon, so an element energy, the external energy must be equal to 0. And remember that this is our equilibrium condition. And if we take the first variation of this equation, we end up with the following. 0 is equal to area B transpose E B U multiplied by the variation in U times T times dA minus the body force NT variation in U and again we have T times dA. We said that gives us the stiffness matrix, that gives us the consistent load vector, and as a final step I can write the following: 0 is equal to K times U minus the consistent load vector variation in U times T times dA. Or let's erase that. Let's say that it's also included in the stiffness matrix. Just write it this way. And from that we get our equilibrium equation, which tells us that in order to evaluate the stiffness matrix, you have to evaluate that integral. And in order to obtain the consistent load vector, you have to evaluate that integral. So in that case, K will be equal to integral B transpose constitutive relationship times B T times dA. This will give you the stiffness matrix, and the consistent load vector is obtained by the body force T times dA. And these are the equations that we have to numerically evaluate to calculate the stiffness and the consistent load vector of a 4-node membrane element. Okay, now let's start talking about the implementation of the quadrilateral membrane element by using the bilinear shape functions. Now, this implementation also was done by using the MATCAD. Now, as we discussed before, we will be using the bilinear shape functions, and these are the equations of the bilinear shape functions, the 4 of them in the natural coordinate system. Now, remember that we did the formulation in the Cartesian coordinate system, but the equations are given here is in the natural coordinate system. So very briefly, let's discuss how we can transform equations written in the natural coordinate system to Cartesian and vice versa. So Cartesian to natural coordinate transformation. Let's briefly discuss that. So let's consider a function f defined in the natural coordinate system. Okay, so I can write the derivatives of this f with respect to psi and nu as follows. Here I'll using the chain rule, so del f over del psi is equal to del f over del x multiplied by del x over del psi plus del f over del y multiplied by del y over del psi. And I can write the same thing for del f over del nu. So del f over del x over del nu plus del f over del y over del nu. So if we write this in matrix form, I have, sorry, let's erase that. Del f over del psi, I have del f over del nu is equal to del x over del psi, del y over del psi, del x over del nu and del y over del nu. And here I have del f over del x, del f over del y. And if you remember that, we call this matrix as J, and it's the Jacobian matrix. Now if I multiply both sides by inverse of the Jacobian matrix, so if we multiply both sides by the inverse of Jacobian, I obtain the following relationship: del f over del x, del f over del y is equal to Jacobian inverse multiplied by del f over del psi and del f over del nu. So in the derivation, remember that we have derivatives with respect to x and y, and by using the following transformation, I can write the x derivation, x derivative in terms of derivatives psi and derivative of nu. How? Let's write that in here. So if I have a function and I'm taking the derivative with respect to x, that will be equal to the first term j11 inverse multiplied by del f over del psi plus j inverse (1,2) del f over del nu. Now del f over del y will then be equal to j21 del f over del psi plus j22 inverse del f over del nu. Okay, so if I have any derivative with respect to the Cartesian coordinate system, I can actually transform that into the natural coordinate system with the following transformation. Okay, so let's come back. Now I have the shape functions here, and these are the derivatives of the shape function with respect to psi and with respect to nu, and I'm just filling a matrix like this. First row has the derivative with respect to psi, and the second row has the derivative with respect to nu. Okay, and if you remember, we made our coordinate interpolation as follows: x is equal to I is equal to 1 to 4 ni xi, and y is equal to I is equal to 4 ni yi, right? So in order to obtain the Jacobian at a certain Gauss point, what I need to do, I need to take the derivative of this function with respect to psi, which is nothing but dn over d psi, this one, multiplied by the x coordinate itself. And the same thing, if I want to take the derivative of y with respect to psi, I have to take derivative of this n with respect to psi, it's right here, and then multiply it with the y. So you will see that my xy matrix has the xy coordinates of each node. So I'm just multiplying it with the derivative function, and I get my Jacobian matrix. Now the next step is the calculation of the strain displacement matrix, right? Remember that this is our B matrix. And we derive the B matrix in terms of derivatives with respect to x and y. Sorry. So here I'm applying the transformation that I write here. Okay, so the first row of the B matrix will have the derivatives with respect to x, so this is what I have. The second row of the B matrix will have the derivative with respect to y, there it is, and the third row will have both the derivative with respect to x and y. Okay, so with this algorithm I'm just filling out the B matrix. Now that's a function for the constitutive relationship. We already have this matrix, I'm just computing it, and remember that this is my E matrix. Now here we are doing a numerical integration. I'm doing 2-point integration because it's a bilinear function, and 2-point integration will give me the exact integration. So these are the psi and nu points, so 4 points we'll have. So at every point, I don't have to do it at every point, you can do it once. At every point I'm calculating the Jacobian, I'm calculating the strain displacement relationship for that particular point, and I'm doing the numerical integration. Here, if you think about it, the Jacobian, determinant of the Jacobian will give me the area of the particular point. And then this is the classical equations. I'm just calculating the degrees of freedom for each node. Now assembling the force vector, and here I'm assembling the global stiffness matrix. And the solution is very straightforward. Calculate the degrees of freedom, number the equations, you can basically say. Calculate the global stiffness matrix, calculate the force vector, and then solve for the displacements. And the final algorithm that I have is the calculating the element forces and stresses. So in this algorithm, I'm just calculating the, for a given element, I'm calculating its xy matrix, the nodal coordinates. Here I'm calculating the element displacement vector. So the nodal forces will be nothing but equal to k times u. So this is the F vector. Then I want to calculate the stresses at every node or every Gauss point. Here I'm calculating stresses at every node. This BP matrix will keep the coordinates of the nodes in the natural coordinate system. I'm calculating the Jacobian again by using the inverse of the Jacobian. I'm calculating the strain displacement relationship B matrix, and for every node I'm calculating the stresses, which is equal to constitutive relationship multiplied with the strain, and that will give me the output as the nodal forces and the stresses. So let's solve an example problem. Now that's a cantilever. These are the material and the sectional properties, and let me give you the answer. So the tip displacement is equal to 0.00237 meters if you just ignore the shear deformations. And if you add the shear deformations to it, your tip displacement will be equal to 0.002402 meters. Okay. Now we know that at support the moment will be equal to 80 kilonewton meters, and of course the shear force will be equal to 20 kilonewtons. So at that support, if I calculate the stress, the axial stress is equal to mc over I. You calculate the I, and then from that we'll obtain the stress as 3330 kilopascal, and the shear stress is equal to shear force divided by the effective area, and that's equal to 20 divided by 0.6 and 0.4. That will give me a shear stress equal to 100 kilopascal. So these are the analytical results that we hope to obtain from our finite element solution. Now the first thing that I'm going to do is I'm going to model this with a single element. Okay. Now with the single element, this is my coordinate matrix, node 1, 2, 3, 4. Sorry, 1, 2, 3, and 4. The restraints, I'm just defining that no translation here at these two nodes. Connectivity matrix, and I'm applying load as follows, 10 and 10. This is the F vector. So the depth is 0.6 and the thickness of my membrane element is 0.4. And the degrees of freedom are as follows here. That's 1, 2, 3, and 4. This is what this matrix is telling me. Then I'm doing the solution. I'm looking at the displacements at degrees of freedom 2 and 4. So these are the displacement. So as you see, the displacement is 1.23 times 10 to the power minus 4, which is almost 20 times smaller than this value. So we see a huge difference in the displacements. And we see huge difference, and when you look at the stresses, they are as expected very small. These are the axial stress at node 1, stresses at node 2, node 3, and node 4, sigma xx, sigma yy, and the shear stress. So we got very small axial stresses, but we expect to see a shear stress in the range of 100 kilopascals. But the stress here is very close to node is equal to 320. So, I mean, this is just garbage. This is not a good solution. But of course, when you look at the nodal displacements, and you obtain it by just k times u. So the axial force is 132 and minus 132, and the moment of these two axial force will give you 80. So it's in equilibrium, and the shear forces, of course, at the nodes. So this is the first node, this is the fourth node. The shear forces balances the input loads. So when you look at the nodes and look at the k times u results, as expected, they satisfy the equilibrium conditions. But when you look at the internal stresses, they are far away from the analytical solution. So we see a huge error in this solution. So, but we know that in the finite element solution, if we use more elements, we will converge to the solution that we are looking for. So let's do that. In that case, let's use 5 elements now. Now this is the discretization. I got 1, 2, 3, 4, 5 elements. And this is the coordinate matrix, the connectivity matrix. So we are following a counterclockwise order for each element. First, restraints, no translations, and at the tip I got 2 point loads in the downward direction, 10 and 10, and the same material properties. So when we look at the degrees of freedom, these are the assigned equation numbers or the degrees of freedoms for each node. So I should be looking at the 6th node, this one, and the 20th node for the tip displacement, and this 10 and 20 should give me the vertical translation. Now I solved it, and I'm looking at the vertical translation. They are equal to 0.0013. So it's better, but this times let's take a look at the actual result. It's this one. This is what we should expect to see. So there are almost 2 times difference. It's not again a good solution, but it's a better solution than a single element. So if I further increase the number of elements, I expect to see a closer result to the finite element. How many elements do I have to use? You don't know unless you try. So the first thing that you need to do in a finite element analysis is to see the mesh sensitivity of the results. So as we keep increasing the numbers, we will see that it will converge to a solution. Now these elements, when you use small coarse mesh, you get very stiff results. So as you increase the number of elements, your the behavior becomes more flexible. So you go from stiff behavior to the flexible behavior and converge to the analytical result. And after a while, you will see not a significant difference, and that's the point where you should know that that's the point to stop. You don't need further elements for solution. Okay. Now when we look at the stresses again, now the axial stress again, the half of what we expect to see, but the shear stress, they are huge, right? We expect to see 100 kilopascals, right, at the support, and I'm seeing a huge, almost 10 times larger stresses. I'm looking at the first element here, so it's these results belong to that element. So there's a problem in the stresses, and even if I use 5 elements, I still far away from the solution. So basically we can say that there's a problem with this element. I mean, 2 times displacement difference is huge for a finite element. It's unacceptable. I have to use much more number of elements, and if you want to converge to the actual results, if you want to try, you can divide these elements maybe like that, and maybe even further. You may have to use like 4 times more elements to get a closer results. So this element has some problems, and we will discuss these problems, and we will see what we can do to further improve the behavior of this element.